So folks, in this example, we want to look at a type of equations called exact equations. We'll give the criteria for what it means to be exact. We'll confirm that equations are exact, and then we'll look at a shortened criteria to see whether or not equations are exact. And then in later videos, we'll learn how to solve them. So without further ado, we're looking at exact ODEs. So remember, we called this form that I've just written this in, this is called differential form. And to determine whether or not an ODE is an exact ODE or not, you first need to write it into differential form, and then you need to do the check. So the check is to find out whether there exists some multivariate function. Here I'm using the Greek letter psi. Don't let that intimidate you. Just for a function, I don't want to use f because sometimes that gets used elsewhere in these problems. Some function psi, so that when we take the partial derivative of psi with respect to x, and another way we can write partial derivative is if we say partial psi partial x, if that is equal to m, and when you take the partial derivative of that multivariate function with respect to y, that is partial psi partial y, if this is equal to n, then the ODE is called an exact ODE, or sometimes an exact equation. So let's first look at this one. In number 3 here, I've given you an ODE. It's already in differential form. It's got that differential x and differential y and various functions. So for example, here we would have that m of xy is the multivariate function y cosine x plus 2x e to the y. And our n of xy is the sine of x plus x squared e to the y minus 1. Well, to determine whether or not this equation is exact, if we were going to check it on our own, we would have to come up with a multivariate function so that when we took the partial derivative with respect to x, we got m, and when we took the partial derivative with respect to y, we ended up with n. Okay? Well, that's actually a pretty challenging task. We'll learn how to do it in just a moment. But here all we're asked to do is to confirm that this ODE is exact when we're given some psi of xy. So let's first check. Let's take the partial derivative of psi with respect to x. So I'm taking this equation here, and remember how you take partial derivatives. You're going to treat, if you're taking it with respect to x, you're going to treat all other variables in the function as a constant. So I'm going to treat this y as just as if it were the number 4 or the letter a or something like that. And same thing with this y and this y when I'm taking the partial derivative with respect to x. So here we go. If we take partial psi partial x, what we end up with is y times the cosine of x plus, and then let's see here, I'm taking the partial derivative of this term right here with respect to x. So that would be 2x, and then that e to the y is just a constant term that plugs along. And then when I take the partial derivative of minus y, well, minus y is a constant term as far as x is concerned, and so the derivative of minus y is 0, so I'll put plus 0. Well, sure enough, look at this. This is the same thing as our m of xy. Likewise, I'm now going to take the partial derivative of this psi with respect to y. So here's our psi. Let me clean this up a little bit. Here's our psi, and I'm going to take the derivative of it with respect to the variable y, which means I'm going to treat all other variables, namely x in this case, as a constant. So this sine of x would be the same thing as if it were, say, the sine of pi over 3 or something like that. I'm going to treat it as just if it were a constant. So when I take the partial derivative of this term, it's a linear term as far as y is concerned. The derivative of a linear term is just its slope, just that constant, so we just end up with the sine of x. When I take the derivative of x squared e to the y, well, the derivative of x squared e to the y with respect to y says treat that x squared as a constant, and the derivative of e to the y is just e to the y, so we get plus x squared e to the y, and then the derivative of a minus y with respect to y is just a minus 1. But look, this is exactly what we called our n of x, and so we have shown that this is an exact ODE. So we'll confirm this in a moment, but it turns out that the solution to an exact ODE, so the implicit solution to an exact ODE, is just to find your psi of xy and then set it equal to your arbitrary constant. That's how we will, that is the solution to any exact ODE. Let's figure out how we could do that. So before we figure out how to find that psi of xy, we're saying this is the solution to the exact ODE. Let's just check that for confirmation. So for our example above, here was our exact ODE. And here on the left-hand side of this expression, this was our psi of xy. And this is a constant, c. So a constant. And this is what we're claiming in number 4. We're claiming, oops, I meant to highlight all of that. We're claiming that this is an implicit solution. This is an implicit solution to this ODE. So let's check that. Okay. So to do so, what we're going to do is we're going to use the technique of implicit differentiation from Calc 1. So what I'm going to do is I'm going to take that ODE and I'm going to take ddx of both sides of it. So we've got ddx and ddx, and we're taking both sides of the, let's see, the right-hand side's a constant, and on the left-hand side we have y sine x plus x squared e to the y minus y. So careful, folks, because we're bouncing back and forth between partial derivatives and regular derivatives. Here again, we are assuming that y is dependent upon x. Okay, so we're back to thinking of y as dependent upon x. And so when we do implicit differentiation, if I take the derivative of an expression in terms of y, there's an implicit chain rule that has to happen there. So let's go ahead and check that. When I take the derivative of this product, we've got the first times the derivative of the second, right? So there's the first factor, there's the derivative of the second. So when I take the derivative of that, I would get the first factor times the derivative of the second factor taken with respect to x, plus the second factor, which is the sine of x, times the derivative of the first factor with respect to x. So for that, I'm going to write dy dx. So that was the derivative right there of that product. For this second product, we've got the first times the derivative of the second. So let's see what we can do here. So that's going to give us, taking the derivative of that second product, there's the first, x squared, times the derivative of the second. What's the derivative of e to the y? Why, it's e to the y times y's derivative, but we represent y's derivative as dy dx. Okay. That was the first times the derivative of the second, but let's complete the product rule. So we've got plus the second, e to the y, times the derivative of the first, which is just 2x. And then finally, we need to take the derivative of this minus y term. So the derivative of minus y with respect to x would be minus 1 dy dx. You certainly don't need that 1 there to hold that place. That's up to you. But then when we take the derivative on the right-hand side, well, there's the right-hand side. The derivative of the right-hand side there is 0. So what have we got? Well, we've got a mess. Our claim was that this whole expression solves this exact ODE. So to check it, we implicitly differentiated both sides. What I'm now going to do is I'm going to group the terms by either y prime terms or non-y prime terms. So let's see here. Grouping together all of my non-y prime terms, I've got y cosine x. That's this term, which has no y prime in it. And then this term, which has no y prime in it. So I'm going to put plus 2x e to the y. And then I'm going to group together all the y prime terms. So I've got that sine of x. I've got this x squared e to the y, and I've got this minus 1. All of that, and let's see here, let me move that over just slightly. Sorry about that, folks. Just a little more room. Times dy dx is equal to 0. So now we're checking to see whether or not this solves the ODE. Notice we are only one step away now from being in that differential form. The trick is to multiply both sides of this equation by differential x formally, and that gives us y cosine x plus 2x e to the y differential x plus the sine of x plus x squared e to the y minus 1 differential y equals 0. And sure enough, we've confirmed that this phi of xy, when set equal to a constant, is in fact a solution to this ODE. So folks, this was rather tedious checking to see, and notice that in order to confirm that this was an exact ODE, I had to tell you what that phi of xy is. In a little bit, you'll figure out how to solve for that phi of xy. But before that, let's give a better criterion for determining whether or not an equation is exact. So let's suppose that we've got an ODE that's already in differential form here. Okay, it's already in this differential form. We can identify the m and the n. Okay, suppose m, n, and then their corresponding partials, as I've written there, are all continuous on some region. then this equation is going to be exact if and only if m sub y is equal to n sub x. Or if you like, in the partial derivative notation, if you take the partial derivative of m with respect to y, is that equal to the partial derivative of n with respect to x? And if this is true, if this is true, then the ODE is exact. So this is saying that we are guaranteed to be able to solve this exact ODE by finding some psi of xy, provided these are all continuous and we have equality of the mixed partials. Derivatives, and I should be a little more careful there, of psi, the original psi, if we have equality of the mixed partial derivatives. Okay? What on earth? Well, let's finish this out here, folks, and then we're going to actually learn the technique for solving these exact ODEs. So first thing is, I just want you to confirm that this is an exact ODE. So first of all, this isn't even in our differential form. So let's multiply both sides by that differential x, and when we do so, we get 2x plus y squared differential x plus 2xy, I'll group that in parentheses just because, differential y equals 0. And so here we can see that our m of xy is the multivariate equation 2x plus y squared, and our n of xy is the 2xy. So there's our n, there's our m. Of course, the naming, it doesn't matter whether you switch your m's and n's, you just have to be consistent. So to check to see whether or not this equation is exact, it's not enough just to put it into differential form. You have to have this equality of mixed partials. So what I'm going to do is I'm going to take the partial, oops, I wanted that to be red. I'm going to take the partial derivative of m with respect to y. Notice that that's the opposite variable than how I grouped this when it was in this differential form. So I'm taking the partial derivative of m with respect to y. So let's see here. 2x gets treated as a constant when I take the derivative with respect to y, so its derivative is 0. And y squared's derivative would be 2y. Likewise, if I take the partial derivative of n now with respect to x, again, that's the opposite variable than what it had been grouped with, because we're checking for mixed partials of our original psi, then we would have, treating our x as a constant, the derivative of this would just be 2y. Notice that we have these two are equal to each other, so the ODE is exact. Okay. The next thing I want to do is give a guess for the above ODE. Let's see if we can guess a solution to this. So we're trying to think of a function that when we take the partial derivative with respect to x, we end up with this expression here. And when we took the partial derivative with respect to y, we ended up with this expression here. Let's see if we can come up with a solution for it. So pause the video and take a guess. And if you can't get it, don't worry, we're going to learn an explicit technique momentarily. Pause the video, take a guess. What's the solution to this ODE? So I went ahead and took a guess at that psi of xy. I guessed that psi of xy would be the function x squared plus xy squared. Let's check that. If you took the partial derivative of this with respect to x, notice that you'd get this expression right here. And if you took the partial derivative of this with respect to y, you'd get this expression up here. So in fact, we have found that psi of xy. And in fact, then we could say that psi of xy set equal to a general constant is a general solution to this exact ODE. So folks, in the next video, I'm going to outline the procedure for actually solving this. So if you weren't able to get this solution just by inspection, don't worry, I'm going to show you some other techniques for doing so. But these other techniques are going to be very similar to, if you've had Calc 3, the techniques we did for finding a conservative vector or potential function for a conservative vector field. So if you had Calc 3, either from me or someone else, you've seen a technique like what we're about to do before, and there is a connection there. And if you're interested, I encourage you to explore that connection between exact ODEs and conservative vector fields. Otherwise, though, I will see you in the next video, and we will learn how to actually solve these exact ODEs.